Step outside on a clear night and look up. The sun is gone, but what replaced it is something stranger. A black ocean filled with stars, each one burning at temperatures that would vaporize any material humans have ever created. Our own sun alone releases energy equivalent to roughly 400 trillion watts every single second. It has been doing that for 4.5 billion years. And yet the space surrounding it, just a few hundred kilometers above your head, hovers near -270 degrees Celsius, cold enough to freeze the air out of your lungs in a fraction of a second. Cold enough that most of the known universe sits just barely above the coldest temperature physically possible. There is a nuclear furnace at the center of our solar system, powerful enough to fuse 600 million tons of hydrogen every single second. And the space it sits inside is nearly as cold as the void can get. This is why the universe is not a warm place bathed in stellar light, but a vast, frozen expanse that barely acknowledges the stars burning inside it. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath, and let's begin. The first thing to understand is that heat is not light. Most people treat them as the same thing because on Earth they almost always travel together. Stand near a campfire, and you feel warmth almost immediately. Step into direct sunlight, and your skin heats up within seconds. The connection seems obvious and automatic. But heat and light are fundamentally different physical phenomena, and the difference between them is the reason space can be flooded with sunlight and still be brutally cold at the same time. Heat, in the scientific sense, is the transfer of energy through the movement of matter. When a flame heats the air above it, the hot gas molecules from the fire collide with the cooler air molecules nearby. They transfer kinetic energy in those collisions. The air molecules speed up. The region gets warmer. This process is called conduction and convection, and both of them require matter, something physical to carry the energy from one place to another. Conduction requires direct contact between materials. Convection requires a fluid, a gas or liquid, that can move and carry thermal energy with it. Both are utterly dependent on the presence of matter. And matter, in the vast reaches of space, is essentially absent. Light is different. Light is electromagnetic radiation. It does not need matter to travel. It crosses the vacuum of space perfectly well. It can travel 150 million kilometers from the sun to Earth without touching a single atom along the way. But here is the crucial part. When light travels through empty space, it does not heat the space itself. It moves through the vacuum without transferring energy to it, because there is nothing there to receive that energy. The photons carry it forward, untouched, until they hit something: a planet, a moon, a spacecraft, a dust grain, a gas molecule. Only at the moment of contact does that energy convert into heat. Space is cold not because the sun is far away. Space is cold because space is empty, and empty things cannot be warm. Temperature, at its most fundamental level, is a measure of motion. Every substance is made of particles, atoms, molecules, electrons. Temperature measures how fast those particles are moving. Hot gas has fast-moving molecules bouncing off each other rapidly. Cold solid has atoms vibrating slowly in their crystal lattice. The higher the temperature, the more kinetic energy the particles carry. Absolute zero, which sits at -273.15 degrees Celsius, is the point at which that particle motion theoretically stops entirely. No vibration, no kinetic energy. The theoretical floor below, which nothing can go. The deep vacuum of space, far from any star, sits at roughly minus 270 degrees Celsius. That is about 2.7 degrees above absolute zero. It is not at absolute zero because of something that fills the entire universe in every direction: the cosmic microwave background radiation. This is the afterglow of the Big Bang itself. When the universe was roughly 380,000 years old, it cooled enough for protons and electrons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was an opaque, glowing plasma. Photons could not travel freely. They were constantly absorbed and re-emitted, trapped in a dense, extraordinarily hot fog. When neutral atoms formed, the fog cleared. Light was suddenly free to travel. That ancient light has been traveling ever since, filling every corner of the observable universe, stretching and cooling as the universe expanded. What began as radiation, with an effective temperature of roughly 3000 Kelvin, has now cooled to just 2.7 Kelvin. It is everywhere. Every cubic meter of space in the observable universe, no matter how remote, is bathed in this relic radiation. And it is this radiation, this 13.8 billion-year-old echo, that keeps the universe from reaching absolute zero. 2.7 Kelvin is about as cold as the universe gets. It is not because of stars. It is because of the beginning. The cosmic microwave background is not just an abstract number. It is physically real in every sense. If you could tune an old-style television set to a channel with no broadcast signal, a small fraction of the static you would see on that screen would be caused by photons from the cosmic microwave background interacting with the antenna. About 1% of that television snow was born in the first moments of the universe. It has been traveling since before the sun existed, since before the Milky Way fully formed, since before the first generation of stars ever ignited. And it arrives at your television antenna today, carrying a message from the beginning of time. The cosmic microwave background fills space uniformly, meaning it arrives from every direction with almost exactly the same intensity. There are tiny variations in its temperature, fluctuations of roughly 1 part in 100,000, that represent the seed structure from which all the galaxies and galaxy clusters in the universe eventually formed. Maps of those tiny fluctuations, made by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, are among the most information-dense scientific images ever produced. They show the universe at its earliest directly observable moment, the pattern of slight overdensities and underdensities in the primordial plasma that gravity would spend the next 13 billion years amplifying into stars, galaxies, and the vast filamentary structures of the cosmic web. But for our purposes, what matters most about the cosmic microwave background is simpler. It is the reason space has a temperature at all. Without it, empty space in thermal equilibrium would be at absolute zero. The cosmic background raises it to 2.7 Kelvin. 2.7 Kelvin is cold in a way that is genuinely difficult to convey. Not metaphorically cold, not cold in the way of a winter morning, but cold in the way that matter barely moves. Cold in the way that most chemical reactions simply do not occur. Cold in the way that every molecular process we associate with life would halt immediately and irreversibly. No enzyme could fold. No cell membrane could maintain its structure. No DNA could replicate. Life, as we understand it, is a phenomenon of moderate warmth. The universe's average temperature is not moderate. It is at the edge of the coldest thing physics permits. To understand why starlight does not warm space, it helps to think about what it actually means for something to have a temperature. Consider a sealed room. You turn on a lamp. The bulb emits light. The light travels to the walls, the floor, the ceiling, the furniture. All of those surfaces absorb some of the radiation and re-emit it as infrared heat. Some of that heat travels back across the room and is absorbed by other surfaces. Back and forth, back and forth. Eventually, the room reaches a thermal equilibrium where everything is at roughly the same temperature. The air in the room warms because it contains countless molecules that absorb radiation and collide with each other, distributing energy throughout the space. The room warms because it is enclosed. The energy has nowhere to go. Now imagine the same lamp, but you remove the walls. You remove the ceiling and the floor. You remove the furniture. You remove the air. The lamp glows in a perfect vacuum with infinite extent. The photons stream outward in every direction. They spread across an ever larger sphere. The intensity at any given distance decreases as the square of that distance, and the space the photons travel through does not warm. There is nothing there to absorb the radiation and re-emit it. There is nothing for the photons to interact with. The photons fly outward forever into a darkness that remains precisely as cold as it was before the lamp was switched on. Stars are that lamp. Space is the infinite room with no walls. The sun burns at millions of degrees in its corona and thousands of degrees at its surface. It has been doing so for 4.5 billion years. In all that time, the deep interstellar medium surrounding our solar system has stayed at 2.7 Kelvin. Not because the sun's energy is gone. It has traveled through that space and continues to do so. But the space itself, the vacuum, has nothing to absorb it and nowhere to hold it. There is a concept in thermodynamics called thermal equilibrium, and it is worth understanding precisely because it clarifies why space never reaches it with the sun. Thermal equilibrium describes a state in which two systems, or two parts of the same system, are at the same temperature because energy has had time to distribute evenly between them. When two objects at different temperatures are placed in contact, heat flows from the hotter to the cooler one until they match. This is not mysterious. It is simply the statistical tendency of energy to spread out. Energy concentrations are unstable. They disperse. In a closed system, a thermos, a perfectly insulating box, a sealed room, the final equilibrium temperature is determined by the total amount of energy divided by the total heat capacity of everything inside. The sun, placed in a perfectly sealed box of space, would eventually warm that box to an equilibrium temperature. But the universe is not a box. It is open, effectively infinite. Every photon the sun emits travels outward and encounters less and less matter as the distance increases. The vast majority of the sun's photons never encounter any significant matter at all before they are so redshifted by cosmic expansion that their energy becomes negligible. There is no thermal equilibrium to reach. The energy simply dissipates, and the space around the sun stays cold. Cosmologists have calculated the total luminosity of all stars in the observable universe. It is a very large number, roughly 5 times 10 to the 44 watts, taking into account all the galaxies and all the stars within them. And yet that total output, spread across the volume of the observable universe, amounts to an average energy density so small that it barely registers above the cosmic microwave background. The math works out to something in the range of a few billionths of a watt per cubic meter of space. An individual flashlight pointed at your face delivers far more power than all the stars in the observable universe contribute to any given cubic meter of space on average. The universe is not dark because the stars are dim. It is effectively cold because the stars are so far apart that their combined output is drowned in the vastness between them. This is also the resolution to a puzzle called Olber's paradox. First clearly articulated in the early 19th century by the German astronomer Heinrich Olbers, though the question was older. If the universe is infinite and uniformly filled with stars, every line of sight from Earth should eventually terminate at a stellar surface. The night sky should be uniformly and blindingly bright as the surface of a star in every direction, like the inside of a furnace. It is not. The night sky is dark. The correct resolution combines two insights. First, the universe is not infinitely old. It has a finite age of about 13.8 billion years. Stars beyond a certain distance are invisible, not because they do not exist, but because their light has not had time to reach us since they formed. The observable universe is limited by the speed of light and the age of the cosmos. Second, the universe is expanding. Light from distant galaxies is redshifted, its wavelength stretched by the expansion of the space it travels through. Photons that began as visible or ultraviolet light arrive as infrared, microwave, or radio waves. Their energy is drastically reduced. The combined effect, finite age and cosmic expansion, means the light from all the stars in the universe amounts to a background radiation field at a temperature of 2.7 Kelvin. The darkness of the night sky and the coldness of space are the same phenomenon. Both are consequences of a universe with a beginning, an ongoing expansion, and a finite age. The night sky is dark because the universe is cold. The universe is cold because it had a beginning and has been expanding and cooling ever since. When the first astronauts stepped outside their spacecraft in low Earth orbit, they encountered something their physics textbooks had described, but that no textbook could fully convey in lived experience. Standing in direct sunlight, the sun-facing side of their suits reached temperatures well above 100 degrees Celsius. Stepping into Earth's shadow, the same suit cooled rapidly toward minus 150 degrees Celsius, all within seconds. On Earth, the atmosphere acts as a thermal buffer. Air absorbs radiation, carries heat through convection, and blankets the planet with an insulating layer that keeps temperatures relatively moderate. Strip away the atmosphere, and you get exactly what space offers: extremes with no middle ground. The sunlit side of Mercury, which has virtually no atmosphere, reaches around 430 degrees Celsius. The night side plunges to roughly minus 180 degrees Celsius. That is a temperature swing of over 600 degrees between one face of a planet and the other. Not because Mercury is particularly unusual, because without an atmosphere, there is no mechanism to redistribute heat. The sunlit rocks absorb the radiation. The dark rocks radiate their heat back into space, and the space between them, even just a few kilometers above the surface, is nearly as cold as it ever gets in the universe. The atmosphere on Earth is one of the most underappreciated features of this planet. It is not just the air we breathe. It is the reason we do not roast during the day and freeze solid at night. The greenhouse gases in that atmosphere, primarily water vapor and carbon dioxide, absorb outgoing infrared radiation and re-emit it in all directions, including back toward the surface. That effect alone raises the average surface temperature of Earth by about 33 degrees Celsius compared to what it would be without an atmosphere. Remove the atmosphere entirely, and Earth's average surface temperature drops from around 15 degrees Celsius to roughly minus 18. The sun would still be shining. The same photons would still be arriving. But with nothing to trap the energy after it has been absorbed and re-emitted by the surface, most of it would leak back into space within hours. What the atmosphere does, in essence, is slow down the escape of energy. It creates a partial barrier between the surface and the cold of space. It keeps heat in the neighborhood long enough for the surface to stay warm. Space has no such mechanism. There is no atmospheric blanket in the interplanetary medium. In space, every photon emitted by a warm surface flies outward into the darkness and is gone. The surface cools. The darkness receives the photon and is, for all practical purposes, unmoved. This is the defining thermal characteristic of the space environment. Energy flows in one direction, from objects to the void, with almost nothing flowing back except the whisper of the cosmic microwave background. And that whisper is cold enough that for most objects near a star, it is the incoming stellar radiation that determines their temperature. But block the star, go into shadow, and the cosmic background reasserts itself. The temperature of a shadowed object begins its long fall toward 2.7 Kelvin. The Sun's outer atmosphere presents one of the most perplexing puzzles in modern solar physics. It is called the coronal heating problem, and it has resisted a fully satisfying solution for more than 80 years. The surface of the Sun, the layer we see when we look at it, called the photosphere, sits at roughly 5,778 Kelvin. That is already hot enough to melt, vaporize, and ionize most known materials. As you move outward from the surface, basic physics suggests the temperature should drop. You are moving away from the source of energy. You are getting further from the nuclear furnace. The temperature should decline. It does, briefly. For the first few hundred kilometers above the photosphere, in the region called the chromosphere, temperatures drop somewhat. The chromosphere is a thin layer, visible as a reddish ring during total solar eclipses, with temperatures ranging from a few thousand up to around 20,000 Kelvin at its upper boundary. Then something goes wrong, by any intuitive understanding of how heat should behave. Above the chromosphere is a thin transition region, just a few hundred kilometers thick, where the temperature jumps dramatically. Over this incredibly short distance, the temperature climbs from around 20,000 Kelvin to over 1 million Kelvin. And beyond the transition region, in the corona, the Sun's outermost atmosphere, temperatures reach between 1 and 3 million Kelvin in typical regions. During periods of intense magnetic activity, some coronal structures reach temperatures of 10 million Kelvin or higher. The corona is several hundred times hotter than the visible surface directly below it. This should not happen. By the basic logic of thermodynamics, a cooler region cannot spontaneously become hotter than the heat source it surrounds. Energy flows from hot to cold, not the other way around. Yet the corona does exactly that. It maintains temperatures hundreds of times higher than the visible solar surface. The corona was first identified as extraordinary through spectroscopic observations in the 1930s and 1940s. Astronomers detected spectral lines in coronal light that corresponded to highly ionized iron atoms stripped of 13 or more of their electrons. Achieving that level of ionization requires temperatures in the millions of degrees. The Sun was surrounded by a shell of gas, millions of degrees hotter than the surface it wrapped around. No one had a convincing explanation for how. Today, the leading explanations involve two main mechanisms. The first is wave heating. The Sun's interior is convective. Enormous cells of hot plasma rise from deeper layers, dump their heat at the surface, cool, and sink back down. This convection creates constant mechanical motion in the photosphere. That motion shakes the footprints of magnetic field lines anchored in the solar interior. The shaking propagates upward along the field lines as waves, specifically as Alfvén waves, a type of magnetic wave that travels along field lines, the way sound waves travel along a taut string. When these waves reach the corona, they interact with its complex, tangled magnetic structure and dissipate their energy as heat. The corona is threaded through with magnetic field lines of all orientations and strengths. When wave energy arrives in this tangled structure, it cascades through increasingly small scales of turbulence, eventually converting to heat at the smallest scales. The second mechanism is nanoflare heating, proposed by the physicist Eugene Parker in the 1980s. Parker proposed that the sun's magnetic field, driven by surface convection, becomes increasingly twisted and tangled over time. When neighboring field lines of opposite magnetic polarity are forced close together, they undergo magnetic reconnection, snapping across and releasing stored magnetic energy as bursts of heat and accelerated particles. Each individual reconnection event is tiny by solar standards, but the rate of nanoflare occurrence across the entire solar surface may be staggeringly high, potentially trillions of events per second across the full corona. The cumulative effect of those tiny energy releases may be what drives coronal temperatures to their extraordinary heights. Neither explanation alone appears complete. More likely, both mechanisms operate simultaneously, with their relative contributions varying across different regions of the corona and at different phases of the solar activity cycle. The Parker Solar Probe, launched in 2018, has been making measurements no spacecraft has ever made before, circling ever closer to the Sun on successive orbits. Its observations have revealed intense, brief magnetic structures called switchbacks, sudden reversals in the direction of the solar wind's magnetic field that hint at energy being released close to the Sun's surface, transported outward by the wind. The Solar Orbiter, launched in 2020 by the European Space Agency, has been providing complementary observations from a different vantage point, building the most complete picture ever assembled of the solar corona's behavior. What the coronal heating problem makes clear is that the Sun's energy delivery to surrounding space is not simple. It is not a steady, uniform broadcast of warmth into an obedient void. It is a complex, turbulent, still not fully understood process that produces regions of extreme energy, sometimes within kilometers of regions at the Sun's nominal surface temperature. The Sun has been shining for 4.5 billion years. Humans have been studying it intensely for centuries. We still do not completely understand how it heats its own outer atmosphere. Beyond the corona, the solar wind carries the Sun's influence outward. But that influence has a boundary. At a certain distance from the Sun, the solar wind pressure becomes too weak to push against the incoming pressure of the interstellar medium. The interstellar medium is the gas and dust that fills the space between stars in our galaxy. The Sun moves through this medium, and the interstellar wind presses inward from all directions. Where the solar wind pressure and the interstellar pressure balance, a boundary forms. This is called the heliopause. It marks the outer edge of the heliosphere, the bubble of space that the Sun controls with its wind and magnetic field. The heliopause sits roughly 120 astronomical units from the Sun, though it is not a perfect sphere. The Sun's motion through the interstellar medium gives the heliosphere an elongated shape, more compressed where the Sun is heading, extended into a long tail in the opposite direction. Before reaching the heliopause, the solar wind passes through a boundary called the termination shock, at roughly 80 to 100 astronomical units. Here, the solar wind, which has been traveling supersonically outward, abruptly decelerates to subsonic speeds as it collides with the accumulated pressure of the interstellar medium. The shock compresses, heats, and slows the solar wind. Beyond it, is a turbulent zone called the heliosheath, where compressed solar wind, plasma churns and mixes before reaching the heliopause. Voyager 1, launched in 1977, crossed the termination shock in 2004 and the heliopause in 2012, after 35 years of continuous travel. Voyager 2, which took a different trajectory through the outer solar system, crossed the heliopause in 2018. When Voyager 1 cleared the heliopause and entered true interstellar space, the change in the particle environment was unmistakable. The density of solar wind particles dropped sharply. The density of interstellar particles increased. The magnetic field direction changed. The spacecraft had left the sun's bubble and entered the cold between the stars. Beyond the heliopause, the sun's warmth becomes negligible. The solar wind drops to zero. The magnetic field that filled the heliosphere ends. What remains is the cold interstellar medium, with its ambient temperature determined not by any nearby star, but by the collective radiation of the entire galaxy. And by that ancient cosmic microwave background. The interstellar medium is not uniform. It contains a range of environments, from cold, dense molecular clouds at temperatures of 10 to 30 Kelvin, to hot, diffuse regions of ionized gas at temperatures of 10,000 to 1 million Kelvin. But even the hottest interstellar regions are extraordinarily sparse, with particle densities far lower than the best laboratory vacuums achievable on Earth. Our own solar system sits inside a region called the local interstellar cloud, a warm, diffuse cloud of partially ionized gas with a temperature of around 7,000 Kelvin. That sounds hot. But the density is less than 1 particle per cubic centimeter. The thermal energy content is negligible. In the sense that matters for objects moving through it, the local interstellar cloud feels nothing like the temperature number implies. The local interstellar cloud is itself embedded in a larger structure called the local bubble, a region roughly 1,000 light-years across, where the interstellar medium is unusually hot and thin. The local bubble appears to have been carved out by a series of supernova explosions over the past 10 million to 20 million years. The shock waves from those explosions swept out the denser gas and dust that originally occupied this region, leaving behind an unusually empty pocket of hot, dilute plasma. Our solar system has been drifting through this bubble for the past few million years. The hot plasma of the local bubble does not heat objects within it. The plasma is too sparse. But it does fill the region with diffuse X-ray emission, visible to space-based X-ray telescopes as a faint glow surrounding our local cosmic neighborhood. It is a reminder that even the seemingly quiet space around our solar system is the aftermath of ancient stellar violence, whose energy is still visible in the X-ray sky millions of years later. The interstellar medium exists in several phases simultaneously, each occupying different volumes and fractions of the galaxy's mass. The coldest and densest phase, the molecular clouds, occupy perhaps 1% of the galactic disk's volume, but contain a large fraction of the gas available for star formation. Cold atomic hydrogen and warm atomic hydrogen together fill much of the galactic disk's mass. Warm ionized gas surrounds hot young stars in regions called HII regions. Hot ionized plasma fills the vast volume above and below the disk in the galactic halo. The transitions between these phases are driven by the energy input from stars. When a massive star forms in a molecular cloud, its ultraviolet radiation ionizes the surrounding gas. When that star ends its life in a supernova, the explosion blasts a shock wave through the surrounding medium, heating it to millions of degrees, compressing nearby clouds, and potentially triggering the formation of a new stellar generation. The interstellar medium is not static. It is a dynamic system, constantly stirred, heated, compressed, and cooled by the stars embedded within it. But on the scales that matter for understanding why space is cold, the verdict is consistent. Most of the volume of interstellar space, most of the time, contains so little matter that temperature itself becomes almost a theoretical concept rather than a physical experience. The discovery of the cosmic microwave background radiation was one of the most important in the history of science, and it came entirely by accident. In 1964, two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were attempting to calibrate a large horn-shaped microwave antenna built for communications with early satellites. They found a persistent background signal they could not explain. It was present in every direction they pointed the antenna. It did not vary with time of day or season. It did not come from the Milky Way. It was not coming from nearby cities. In frustration, they found a pair of pigeons had been nesting in the antenna and removed both the birds and what they diplomatically described as a white dielectric material. They recalibrated. The hiss remained. Meanwhile, a few dozen kilometers away at Princeton University, a group of physicists, including Robert Dicke and Jim Peebles, had recently worked out that if the Big Bang model was correct, the universe should be filled with a faint radiation field, the cooled remnant of the hot plasma that filled the early universe. They predicted its temperature. They were building an antenna to detect it. When the Princeton group learned of the Bell Labs signal, the connection was immediate. Penzias and Wilson had found what the Princeton group was looking for: the cosmic microwave background, the afterglow of the Big Bang, the oldest light in the universe. The discovery confirmed that the universe had a hot, dense beginning. It confirmed that the Big Bang was not merely a theoretical convenience, but a historical event whose echo was still measurable today. Penzias and Wilson received the Nobel Prize in Physics in 1978. The temperature they measured was around 3.5 Kelvin, consistent with later, more precise measurements of 2.725 Kelvin. The cosmic microwave background is not simply radio noise. It is the oldest, directly observable signal in the universe, carrying information about conditions when the universe was less than 400,000 years old. Before it was released, for the first 380,000 years of cosmic history, the universe was opaque, a fog so dense that no photon could travel freely. The moment of its release is called the surface of last scattering. Everything we can observe with our telescopes came after that moment. Everything before it is, in principle, hidden from direct observation. The cosmic microwave background fills space uniformly in every direction. It is the reason space has a minimum temperature at all. Without it, an object in perfect isolation, shielded from all radiation sources, would continue radiating its own heat outward and cooling toward absolute zero, with nothing to stop it. The cosmic microwave background is that stopping point. The cold you conceptually associate with space, the minus 270 degrees of the void, is not the absence of the Big Bang's energy. It is the last whisper of it, stretched thin across 13.8 billion years of cosmic expansion. There is a related phenomenon that governs temperature on every airless body in the solar system. The temperature any body reaches in sunlight depends on a balance between how much solar radiation it absorbs and how fast it re-radiates that energy as heat. The sun delivers about 1,361 watts per square meter at Earth's orbital distance. A perfectly black body placed there would reach an equilibrium temperature of roughly 279 Kelvin, just above freezing. Real bodies have a property called albedo, a measure of reflectivity. Fresh snow reflects about 90% of incoming sunlight. Dark volcanic basalt reflects roughly 5%. The lower the albedo, the more radiation is absorbed, the higher the equilibrium temperature. The Moon has an average albedo of about 12%. Earth has an average albedo of about 30%, largely because of its cloud cover. Venus, shrouded in highly reflective sulfuric acid clouds, has an albedo of about 65%, yet its surface temperature is over 460 degrees Celsius because its dense carbon dioxide atmosphere creates an extreme greenhouse effect. The comparison of Earth and Venus is one of the most instructive in planetary science. Both orbit within the inner solar system. Both receive significant solar radiation, but one is comfortable for liquid water and life. The other is hot enough to melt lead on its surface. The difference is almost entirely in the atmosphere. The greenhouse effect on Earth is mild and life-sustaining. On Venus, it is catastrophic and planet-sterilizing. The same physical process, operating at different intensities, produces entirely different worlds, and in space, without any atmosphere at all, neither process operates. Objects absorb and emit radiation directly. The vacuum between them is indifferent to both. The James Webb Space Telescope, which launched in December 2021, is one of the most thermally sensitive instruments ever built. It operates at around -233 degrees Celsius, 40 Kelvin. It has to. Its infrared detectors need to be cold to detect the faint heat signatures of the most distant galaxies in the universe, of exoplanet atmospheres, of star-forming regions hidden behind curtains of dust. Even a small amount of unwanted thermal emission from the telescope itself would overwhelm the signals it is designed to detect. The telescope sits at the second Lagrange point, roughly 1.5 million kilometers from Earth in the direction away from the Sun. A large sun shield, roughly the size of a tennis court when fully deployed, blocks radiation from the Sun, Earth, and Moon simultaneously. It is constructed from 5 layers of a highly reflective material. Each layer reflects the incoming solar radiation. The small amount of heat that penetrates from one layer to the next is radiated sideways into space before it can reach the telescope structure. The sun-facing side of the outermost shield layer reaches a temperature of about 85 Kelvin. The side facing away, where the telescope's mirrors and instruments sit, cools passively to around 40 Kelvin simply by radiating its residual heat into the cold vacuum of space. Space itself is the refrigerator. No powered cooling systems are needed to reach those temperatures for most of the telescope's structure. Space is cold enough to pull the heat out through radiation alone. This is a theme in the design of every infrared observatory ever built. Cold is not the enemy. Cold is the tool. The frigid vacuum that would end any biological organism in moments is, to an infrared telescope, the ideal operating environment. It is the reason we can observe the heat signatures of galaxies formed less than 1 billion years after the Big Bang. It is the reason we can detect the faint atmospheric signatures of a planet orbiting another star, many light-years away. The coldness of space is not a problem to overcome. It is the very property that makes some of the most remarkable science in human history possible. Objects in space warm up through radiative heating and lose heat through radiative cooling. In the vacuum, these are the only 2 mechanisms available. No conduction, no convection. Only radiation in, radiation out. Spacecraft engineers spend enormous effort managing this balance. A spacecraft facing direct sunlight can reach temperatures that damage electronics or optical systems. In shadow, the same spacecraft can cool to temperatures that affect battery performance, lubricants, and mechanical components. The solution in most spacecraft is a combination of surface coatings, multi-layer insulation, and in some cases, small electric heaters that keep sensitive components above their minimum operating temperatures during shadow passages. Radiator panels, surfaces designed to dump excess heat efficiently into the cold of space, handle the other extreme during sunlit periods. It is a constant balancing act, managed autonomously by onboard thermal control systems throughout the life of every spacecraft ever built. The Apollo astronauts on their way to the moon experienced the thermal management problem in an unusually direct way. The command module orbiting the moon passed in and out of lunar shadow regularly, with the sunlit side heating and the shadowed side cooling rapidly. Mission planners had to ensure the spacecraft's thermal control systems could handle those cycles without hardware failure. The solution included a technique called passive thermal control, a slow roll of the spacecraft around its long axis that kept any one side from heating too much or cooling too long. The astronauts and engineers called it the barbecue roll. It was a purely thermal management maneuver designed to distribute solar heating evenly across the spacecraft's surface. It worked because space is cold. If space were thermally moderate, the roll would have been unnecessary. The extremes of temperature in the near-Earth space environment, the swings from above boiling to well below freezing with every orbit or shadow transit, are entirely products of the same fundamental physics: radiation in, radiation out, with a cold void providing no buffer between the two extremes. The spacesuit used during spacewalks from the International Space Station contains elaborate thermal control systems to manage these same extremes at the human scale. Water is circulated through a network of tubes in a garment worn against the skin, carrying heat away from the body. That water is then cooled by a device called a sublimator, which vents water into the vacuum of space, where it instantly freezes and then sublimes directly from solid to vapor, carrying heat away in the process. The cold of space is being used directly as a cooling resource. The frigid vacuum that would end an unprotected human in seconds is, in the thermal engineering of the spacesuit, the solution to the thermal management problem it otherwise poses. This is one of the stranger aspects of working in space. The environment that threatens you is also the tool you use to survive it. The coldness that would end your life in seconds is simultaneously the coldness that keeps your cooling system working. There is a phenomenon that illustrates the separation between radiation and temperature in space with particular elegance. It is called the Yarkovsky effect. Small asteroids and rocky bodies in space experience a tiny but measurable force due to the asymmetric re-emission of thermal radiation. As a rotating asteroid absorbs sunlight during its dayside, its surface warms. As it rotates into its nightside, that warmed surface radiates the stored heat back into space as infrared photons. But because the asteroid has rotated, the nightside surface is no longer pointing directly away from the sun. The thermal emission is offset from the direction of incoming solar radiation by an angle determined by the asteroid's rotation rate and thermal properties. This asymmetric emission acts like a tiny rocket exhaust, pushing the asteroid very slightly in a direction determined by its rotation. Over millions and billions of years, constant small forces produce large effects. The Yarkovsky effect can shift an asteroid's orbital semi-major axis by hundreds of thousands of kilometers over 1,000,000 years. It has been measured directly on several near-Earth asteroids. The asteroid Bennu, visited by the OSIRIS-REx mission in 2019 and 2020, was found to be drifting in its orbit at a rate consistent with Yarkovsky acceleration. Asteroid Apophis, which will make a close approach to Earth in 2029, has a Yarkovsky drift that must be accounted for in precise orbital predictions. The Yarkovsky effect works only because space is cold. The asteroid heats up in sunlight and then radiates that heat into a cold vacuum. The temperature difference between the sunlit and shadowed sides creates the asymmetry that drives the force. If space had a significant ambient temperature, if the background radiation were warm enough to compete meaningfully with solar input, the temperature contrast across the asteroid would be reduced and the Yarkovsky force would weaken. The Yarkovsky effect is a measurable consequence of the fact that space is cold enough that the sun's radiation dominates completely over the background at the scale of our solar system. The distribution of near-Earth asteroids, the structure of the asteroid belt itself, the delivery of meteorites to Earth, all of these are influenced over geological time by the Yarkovsky effect. The cold of space shapes the solar system in ways far beyond the obvious. The solar wind that streams outward from the corona carries extreme temperatures in its particles. By the time the solar wind reaches Earth's orbit, its protons have temperatures of around 100,000 Kelvin, and its electrons can reach millions of Kelvin. These are real temperatures in the technical sense. The particles are genuinely moving at speeds corresponding to those kinetic energies. But the solar wind near Earth's orbit contains roughly 5 to 10 protons per cubic centimeter. That density is so extraordinarily low that the concept of temperature, in the sense of something that can warm an object, barely applies. Temperature in a dense gas describes the average energy of enormous numbers of colliding molecules. In the solar wind, particles travel vast distances without colliding with anything. A proton in the solar wind may travel hundreds of thousands of kilometers before encountering another particle. In a gas, like Earth's atmosphere, a molecule at room temperature collides with neighbors roughly 10 billion times per second. These collisions are the mechanism by which thermal energy spreads and equilibrates. Remove the collisions, and you remove the thermal physics we are familiar with. The solar wind is hot in the way that a single bullet is hot. The kinetic energy is real, but there is not enough of it in any given volume to meaningfully warm anything. If you placed a thermometer probe in the solar wind and waited long enough, it would come to equilibrium, not with the particle temperature of the wind, but primarily with the incoming solar radiation from the sun. The radiation density at Earth's orbit is far higher in terms of energy per cubic meter than the kinetic energy of the sparse plasma. The photons dominate. The thermometer reads the radiation temperature, not the plasma temperature. This is why spacecraft near Earth are not heated to 100,000 degrees by the solar wind. The photons warm them to a few hundred Kelvin. The plasma, despite its technical temperature, passes by almost unnoticed. There is something almost philosophical about the relationship between the sun and the cold of space. The sun is an almost incomprehensible engine of energy production. Nuclear fusion at its core converts 4 million tons of mass into pure energy every single second. That energy radiates outward through the solar interior over a journey that takes tens of thousands of years before it reaches the surface. It escapes as visible light, infrared radiation, ultraviolet radiation, X-rays, and the solar wind. All of it streams outward into a universe that is, for all practical purposes, infinite. And the universe receives it without warming. The cold of space is not emptiness in the colloquial sense of something missing. It is the natural resting state of the cosmos. Left to itself, with no energy input, the universe would continue cooling as it expands, asymptotically approaching absolute zero over astronomical timescales. Stars are the disruption. They are temporary islands of intense energy in a sea that was always cold and is slowly returning to cold. The warmth we experience here on Earth is not the normal state of the universe. It is a local exception. A brief, fortunate consequence of living near a star that formed at the right time, at the right distance, on a planet with the right atmosphere to trap some of its heat. Remove any one of those factors, and the cold of space reasserts itself immediately. The sun will not burn forever. It has roughly 5 billion years of hydrogen fuel remaining in its core. When that fuel is exhausted, the sun will swell into a red giant, dramatically changing the energy environment of the inner solar system. Eventually, it will shed its outer layers and collapse into a white dwarf, a dense, slowly cooling remnant roughly the size of Earth, containing roughly half the sun's current mass. White dwarfs cool for trillions of years, radiating the last of their stored heat into the cold of space. On timescales of 100 trillion years, the last stars will exhaust their fuel and fade. The universe will enter a long dark age in which the only remaining sources of energy are the slow processes associated with black hole decay, through what is known as Hawking radiation. Eventually, on timescales that are barely expressible in numbers a human mind can hold, even the last black holes will be gone. What remains will be an extremely cold, extremely thin sea of particles drifting in an expanding universe. The universe will be, for all practical purposes, at absolute zero. Everything we know, every star, every galaxy, every planet, every structure more complex than a single particle, is a temporary deviation from that final cold. We are living in the warm afternoon of the universe. The morning was the Big Bang. The evening will be very long and very, very cold. Step back one final time and look at the universe as a whole. The observable universe extends roughly 46 billion light-years in every direction from Earth. Within it are somewhere between 200 billion and 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Those stars collectively radiate an almost unimaginable total amount of energy, and yet the average temperature of the universe is 2.7 Kelvin, just barely above absolute zero. All of that stellar output spread across the volume of the observable universe, diluted by expansion over 13.8 billion years, amounts to an energy density so small that space sits at the edge of the coldest temperature that physics allows. The universe is not a warm place. It is a frozen void with small, intensely hot pockets. Those pockets are separated by distances so vast that their warmth barely registers in the space between them. The nearest star to our Sun is Proxima Centauri, about 4.24 light-years away. In the entire volume of space between our Sun and its nearest neighbor, the temperature of the ambient medium barely rises above 2.7 Kelvin. The Sun burns at thousands of degrees at its surface and millions in its corona. Its light and wind pour outward in every direction, and the space, just a fraction of the way toward the nearest star, is essentially undisturbed. Not because the Sun is dim, because space is vast, and because photons traveling through vacuum do not leave warmth behind them. In the Boomerang Nebula, a young planetary nebula located about 5,000 light-years from Earth in the constellation Centaurus, astronomers have measured temperatures of approximately 1 Kelvin, colder than the cosmic microwave background itself. This makes the Boomerang Nebula the coldest known natural environment in the observable universe. A dying star at its center is expelling gas at an enormous rate and accelerating it outward at around 164 kilometers per second. As the gas expands rapidly into the surrounding vacuum, it cools through adiabatic expansion. The same process that makes the air from a pressurized aerosol can feel cold when it expands. The expansion is so rapid that the gas cools faster than the cosmic microwave background can reheat it. The result is a natural refrigerator in space, creating conditions colder than the Big Bang's own afterglow. The universe's extremes of temperature exist simultaneously in the same cosmic neighborhood, the hot and the cold separated by nothing more than the boundaries of matter. There is a related question that the coldness of space raises for anyone who thinks carefully about energy in the future. Where does all the sun's energy actually go? The sun has been releasing roughly 3.8 times 10 to the 26th watts for 4.5 billion years. That is a number so large it is essentially meaningless without context. To get a sense of scale, consider that the entire global energy consumption of human civilization amounts to roughly 2 times 10 to the 13 watts. The sun's output exceeds that by a factor of roughly 20 trillion every second. All of this energy streams away from the sun in every direction. A tiny fraction of it, roughly 1 part in 2 billion, is intercepted by Earth. Even smaller fractions are intercepted by the other planets, their moons, the asteroids and comets, and dust that populate the solar system. The vast majority, more than 99.9% of the sun's total output, passes through the solar system without hitting anything at all. It crosses the heliopause, enters interstellar space, and continues. The photons from our sun will travel until they are absorbed by something. A dust grain in a distant molecular cloud, the atmosphere of a planet orbiting a far star, the surface of a rogue asteroid drifting between galaxies. Or until they are so stretched by the expansion of the universe that their energy effectively drops to zero. The energy does not disappear. It becomes increasingly spread out across an increasingly large volume of space. It contributes, in an infinitesimal way, to the background radiation field of the cosmos, and the temperature of that cosmos remains 2.7 Kelvin. All of that stellar output, across the entire observable universe, across the entire history of stars, amounts to a background temperature that has barely moved since the cosmic microwave background first set the floor. This is not because stars are inefficient. It is because the universe is extraordinarily large, and because the energy released by stars is a rounding error compared to the volume it has to fill. Understanding this also illuminates the future of our solar system in a more personal way. Earth sits in a privileged zone around the sun. Not so close that the solar radiation boils the oceans away, not so far that it freezes the surface permanently. The region where liquid water can exist on a planetary surface is called the habitable zone, and Earth sits near its inner edge. But the sun is not static. Like all main sequence stars, it is slowly growing brighter as it ages. In the sun's early years, roughly 4 to 4.5 billion years ago, it was about 70% as luminous as it is today. This raises a puzzle that paleoclimatologists and geologists have grappled with for decades, called the faint young sun paradox. If the sun was significantly dimmer in the deep past, Earth's surface should have been frozen. Liquid water requires a certain minimum of incoming energy. But the geological record shows liquid water and even signs of warm oceans extending back to at least 3.8 billion years ago and possibly earlier. The resolution appears to lie in the early Earth's atmosphere. Higher concentrations of greenhouse gases, particularly carbon dioxide and methane, would have compensated for the dimmer sun by trapping more of what heat there was. As the sun gradually brightened, geological processes slowly drew down those greenhouse gas concentrations, keeping Earth's temperature roughly stable despite the changing solar output. It was a long-running, geologically managed balancing act. A thermostat operated by carbon cycles and volcanic outgassing over billions of years. Looking forward, the sun will continue brightening. Over the next billion years, its luminosity will increase enough to make Earth's surface increasingly uncomfortable for the complex life that currently inhabits it. The same greenhouse effect that currently keeps Earth warm enough for life will become increasingly problematic as the sun delivers more energy to the surface. In roughly a billion years, the conditions that have sustained life as we know it will begin to change irreversibly. This is not an immediate crisis by any human measure, but it is a reminder that the thermal balance of Earth, the comfortable middle ground between the sun's heat and the cold of space, is not permanent. It is a temporary equilibrium maintained by a specific combination of solar luminosity, planetary distance, atmospheric composition, and geological processes that will not remain in their current configuration indefinitely. The warmth we depend on is real, but it is borrowed. The physics of why space is cold also has direct implications for how we search for life elsewhere in the universe. When astronomers hunt for potentially habitable planets around other stars, the primary criterion is distance from the host star. Is the planet in the habitable zone? Is it receiving enough stellar radiation to maintain liquid water on its surface? But the habitable zone is not a fixed concept. It depends on the type of star. For a dim red dwarf star, which are the most common type of star in the galaxy, the habitable zone sits far closer to the star than Earth sits to the sun. Planets in the habitable zone of a red dwarf orbit at distances of a few million kilometers, rather than 150 million. At those close distances, tidal forces from the star are significant. Many such planets may be tidally locked, always showing the same face to their star, the way the moon always shows the same face to Earth. The day side bakes in perpetual sunlight. The night side freezes in perpetual darkness. The same physics applies. The side facing the star heats up in its radiation. The side facing away radiates heat into the cold of space, and without a thick enough atmosphere to redistribute heat around the planet, the temperature differences would be extreme. Whether life could survive on such a planet depends critically on whether the atmosphere is substantial enough to transport heat from the day side to the night side. A thin atmosphere or no atmosphere, and the night side is essentially part of the cold of space, permanently frozen. A thick enough atmosphere and the temperature differences diminish, creating a more habitable global environment. The same principle that governs the temperature of Mercury, of the Moon, of a spacecraft in orbit, governs the habitability of planets around other stars. The cold of space is not just a curiosity of our own solar system. It is a universal constraint on where life can exist. Everywhere in the universe, life, if it relies on liquid water and chemical reactions, requires protection from the cold of the vacuum. It requires an atmosphere to trap heat, a star to supply it, and an orbit at the right distance to balance the two. Life, if it exists elsewhere, is probably clinging to warm rocks surrounded by the same cold void that surrounds ours, protected by the same physical accident of atmosphere and proximity, vulnerable to the same fundamental physics. Temperature requires matter. Cold is the default. Warmth is the exception that has to be engineered by planetary geology, stellar proximity, and atmospheric chemistry working in concert. The energy budget of the entire Earth is worth understanding precisely because it illustrates so clearly how the thermal balance between the Sun and the cold of space actually works. Incoming solar radiation at Earth's orbit amounts to about 1,361 watts per square meter on a surface perpendicular to the Sun. Earth is a sphere, and only 1/4 of its surface faces the Sun at any given time, so the average solar input across the whole planet's surface is about 340 watts per square meter. Of that incoming energy, about 30% is reflected directly back into space by clouds, the atmosphere, and bright surfaces. This reflected fraction, the albedo, contributes nothing to Earth's temperature. The remaining 70% is absorbed. About 23% is absorbed by the atmosphere. About 47% reaches and is absorbed by the surface. The absorbed energy warms the surface and the atmosphere. The warmed surface re-emits energy as infrared radiation. Some of that infrared radiation escapes directly into space. Some is absorbed by greenhouse gases in the atmosphere, which then re-emit it in all directions, including back toward the surface. This greenhouse re-emission is the mechanism that raises Earth's surface temperature above what it would be otherwise. In steady state, Earth emits exactly as much energy as it absorbs. If it absorbed more than it emitted, it would warm until the increased thermal emission balanced the input. If it emitted more than it absorbed, it would cool until the reduced emission matched the absorption. The equilibrium temperature is the temperature at which incoming absorbed radiation exactly equals outgoing emitted radiation. For Earth as a whole, this works out to a surface temperature that supports liquid water, moderate weather, and biological activity. Change the composition of the atmosphere, and you change the greenhouse trapping, shifting the equilibrium temperature up or down. Change the distance from the Sun, and you change the input, shifting the equilibrium temperature. Change the albedo, and you change how much of the input is absorbed versus reflected. Every planet in the solar system reaches its own equilibrium through this same process. And in every case, the cold of space is the ultimate destination for all the energy that is not retained. It is the sink that the entire solar system radiates into. It is the reason any equilibrium temperature is stable rather than runaway. The Sun keeps putting energy in. Space keeps drawing energy out. The surface temperature of any planet is the balance point between those two flows. And space is so cold that even the combined output of the Sun is insufficient to warm it. The balance is, overwhelmingly, in favor of the cold. Earth's warmth is a thin film of temperature maintained against an essentially infinite cold surrounding it on all sides. The concept of blackbody radiation is worth pausing on, because it explains with precision how objects in space determine their own temperature. Any object with a temperature above absolute zero emits electromagnetic radiation. Not just hot objects. Every object. A block of ice emits radiation. A cold asteroid emits radiation. Even an object cooled to just a few kelvins still emits a tiny amount of radiation. The wavelength distribution of this emitted radiation depends on the temperature. Hot objects emit more radiation at shorter wavelengths, visible light and ultraviolet. Cooler objects emit at longer wavelengths, infrared, microwave, radio. The relationship between temperature and peak emission wavelength was worked out by the German physicist Wilhelm Wien in the 1890s and is called Wien's displacement law. For the Sun's photosphere at about 5,778 Kelvin, the peak emission wavelength falls in the visible range, around 500 nanometers, yellow-green light. This is not a coincidence. It is almost certainly the reason human eyes evolved to be most sensitive to yellow-green light. We evolved under a star whose peak emission is at that wavelength. Our visual systems were tuned by natural selection to the dominant radiation from our local star. For Earth's surface at around 290 Kelvin, the peak emission falls in the infrared, around 10 micrometers, completely invisible to the naked eye, but detectable by infrared cameras. This is the radiation that escapes through the atmosphere into space, and eventually reaches the cold of the cosmic background. For the cosmic microwave background itself, at 2.7 Kelvin, the peak emission falls at around 1 millimeter wavelength. Microwave radiation, the oldest light in the universe, now stretched so far that it emits at the same wavelengths used by some kitchen appliances. The spectrum of an object's thermal emission is one of the most powerful tools in astrophysics. It tells you the temperature of anything you can observe, from the nearest asteroid to the most distant galaxy. It tells you the temperature of a planet's atmosphere by analyzing how its emission spectrum deviates from a perfect blackbody curve. It tells you the temperature of the cosmic microwave background with extraordinary precision. And it tells you, from first principles, that any object in deep space that is shielded from all external radiation sources will eventually cool to 2.7 Kelvin as it radiates its heat into the cosmic background and reaches equilibrium with it. 2.7 Kelvin is not just the temperature of space. It is the final resting temperature of everything, given enough time and isolation. It is the universe's way of saying that all the energy released by all the stars that have ever burned will eventually spread thin enough to be indistinguishable from the background. All the light, all the heat, all the stellar fire ends at 2.7 Kelvin. The sun's relationship with the cold of space becomes even more interesting when you consider the solar cycle. The sun is not a constant source of energy. It varies. Over an 11-year cycle, the sun's level of magnetic activity rises and falls. At solar maximum, the sun's surface is covered with sunspots, active regions, and frequent eruptions called solar flares and coronal mass ejections. At solar minimum, the surface is comparatively quiet. The sun's total energy output varies by about 0.1% between solar maximum and solar minimum. This tiny variation, 1 part in 1,000, is enough to have a measurable influence on Earth's climate over multi-decade timescales. Historical periods of prolonged solar minimum, like the Maunder minimum that lasted from roughly the 1640s to the early 1700s, have been correlated with cool periods in Earth's climate history. The Maunder minimum corresponded with some of the coldest decades of the period called the Little Ice Age, when average temperatures in Europe and North America were noticeably lower than surrounding centuries. Whether the solar output change was the primary cause of the cooling or merely a contributing factor is still debated. But the correlation is real, and it demonstrates that even small changes in the sun's energy output translate into measurable changes in Earth's temperature. The sun also emits intense bursts of energy during solar flares and coronal mass ejections. A major flare can release energy equivalent to 1 billion hydrogen bombs in a matter of minutes. A coronal mass ejection can hurl billions of tons of plasma into the solar system at speeds of hundreds to thousands of kilometers per second. When these events are directed toward Earth, they can compress Earth's magnetosphere, drive strong currents in Earth's ionosphere, and in severe cases affect power grids and communication systems. The most powerful geomagnetic storms on record, caused by coronal mass ejections striking Earth, have disrupted telegraph systems, caused widespread auroras visible at unusually low latitudes, and in modern times have threatened the safety of spacecraft and power infrastructure. Yet for all the drama of these events, the space between the Sun and Earth remains at 2.7 Kelvin in the regions not directly swept by the plasma. The plasma itself, the coronal mass ejection, is hot by particle speed. The vacuum it travels through is cold. The two coexist. The plasma passes through the cold vacuum the same way a hot bullet passes through cold air. The medium does not adopt the temperature of the object moving through it. The object simply moves through the medium, and the medium continues as it was. There is a profound connection between the cold of space and the arrow of time. The second law of thermodynamics states that in any isolated system, entropy, roughly, the degree of disorder, tends to increase. Energy spreads out. Hot things cool. Concentrated energy disperses. This tendency is not a law in the sense of a rule imposed from outside. It is a statistical reality. There are vastly more ways for energy to be spread out than concentrated. A spontaneous movement from spread out to concentrated is not impossible in principle. It is merely so astronomically unlikely as to never occur in practice. The universe began, at the Big Bang, in a state of extraordinarily low entropy for its energy content. Everything was concentrated, incredibly hot, incredibly dense. Since then, the universe has been expanding, cooling, and moving toward higher entropy states. Stars are temporary reversals of this trend. Gravity concentrates matter into dense clouds, which collapse and heat to stellar temperatures, which fuse hydrogen and release the energy. Stars are pockets of concentrated energy forming in a universe that is, overall, dispersing its energy. They are local decreases in entropy paid for by larger increases in entropy elsewhere. The light and heat that a star radiates into the cold of space is entropy increasing. The concentrated nuclear energy in the stellar core disperses into an enormous volume of nearly empty cold space. The star is the temporary exception. The cold void is the thermodynamic destination. This is why the sun is hot and space is cold, stated in the most fundamental terms possible. The sun is a concentration of energy that formed because gravity is strong and the universe started in a low entropy state. Space is cold because entropy tends to increase, energy tends to spread, and an essentially infinite universe provides effectively infinite room for that spreading. The cold of space is not a puzzle. It is thermodynamics made visible. It is the universe doing what the universe does, moving, inexorably and continuously, toward the state where all the energy is as spread out as possible. We are living near one of the temporary bright spots in that process. And we are warm because of it. The concept of absolute zero itself deserves a closer examination, because it reveals something fundamental about the relationship between temperature and the physical world. Absolute zero is not simply very cold. It is a physical limit, a boundary defined by the nature of matter itself. Temperature is, at its root, a measure of the average kinetic energy of particles. When you lower the temperature of a substance, you are removing kinetic energy from its particles. They slow down. They vibrate less. They interact with their neighbors less energetically. The question that naturally arises is, what happens when all the kinetic energy is gone? When the particles stop moving entirely? The answer, from classical physics, is absolute zero. But quantum mechanics introduces a complication that makes absolute zero even more interesting. Quantum mechanics places a fundamental limit on how precisely you can simultaneously know the position and velocity of any particle. This is called the Heisenberg uncertainty principle. If a particle were truly at rest, if its velocity were precisely zero, you would know its momentum exactly. But knowing the momentum exactly means the uncertainty in its position becomes infinite. The particle could be anywhere. This is not just a limitation of our measuring instruments. It is a fundamental feature of physical reality. A consequence is that particles always retain what is called zero-point energy, a minimum irreducible amount of kinetic energy that cannot be removed regardless of how cold the surroundings become. Helium, the lightest of the noble gases, cannot be frozen into a solid at atmospheric pressure, even at temperatures just fractions of a degree above absolute zero. The zero-point energy of its atoms is enough to keep them moving and prevent them from locking into a crystalline lattice. You have to apply significant pressure to force helium into a solid state. This zero-point motion is real. It has measurable consequences, and it means that true absolute zero, a state of completely zero kinetic energy, is not achievable in practice, and arguably is not even definable in the quantum mechanical description of reality. The universe at 2.7 Kelvin is cold beyond everyday experience, but it is not at absolute zero. It is not even close to the temperatures achieved in advanced laboratory settings, where physicists have cooled tiny samples of atoms to within a billionth of a degree of absolute zero, the coldest temperatures ever achieved on Earth. In research laboratories using techniques like laser cooling and evaporative cooling, are far colder than the cosmic microwave background. In those experiments, atoms are cooled to temperatures of 10 to the minus 9 Kelvin, a billionth of a degree above absolute zero. At those temperatures, atoms move so slowly that their quantum wave-like nature becomes dominant. Groups of atoms enter a state called a Bose-Einstein condensate, where they collectively behave as a single quantum entity rather than as individual classical particles. The physics of these ultra-cold systems has produced extraordinary discoveries and has practical applications in precision measurement, quantum computing, and atomic clocks. The coldest temperatures in the universe, by this measure, are not in the deep void of interstellar space. They are in Earth-based physics laboratories. And even those laboratory temperatures cannot reach the theoretical floor of absolute zero. Space at 2.7 Kelvin is cold, but it is warmer than a physics experiment. The universe, vast and ancient and mostly empty, is not quite as cold as it could be. And the reason it stops where it does, at 2.7 Kelvin rather than at zero, takes us back to the beginning. To the moment 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light was freed to travel. That ancient light is still here, still filling every corner of the observable cosmos, still setting the floor. When astronomers and physicists talk about the thermal history of the universe, they trace a story that runs from extraordinary heat to near absolute cold over 13.8 billion years. The universe began in a state of temperature so extreme that our current physical theories cannot fully describe it. In the first fractions of a second after the Big Bang, the temperature exceeded 10 to the 32 Kelvin, the Planck temperature, beyond which quantum gravity effects dominate and our standard physics breaks down. As the universe expanded, it cooled rapidly. By the time it was 1 second old, the temperature had fallen to about 10 billion Kelvin, still hot enough for nuclear reactions to occur. The protons and neutrons formed in the first second began fusing into light atomic nuclei, hydrogen, helium, and traces of lithium. This process, called Big Bang nucleosynthesis, was complete within the first few minutes. By 3 minutes, the universe had cooled enough that the nuclear reactions stopped. The ratio of hydrogen to helium was fixed at roughly 3:1 by mass. That ratio, the fundamental fingerprint of the Big Bang, is still visible today in the oldest and most pristine stars. whose compositions reflect the primordial mix of elements before any stars had time to alter it. Over the next several 100,000 years, the universe continued expanding and cooling. The temperature fell from billions of degrees to thousands. The photons became less energetic. Eventually, at around 300,000 to 400,000 years after the Big Bang, the temperature fell to about 3,000 Kelvin. At that temperature, the photons no longer had enough energy to ionize hydrogen atoms. Electrons and protons combined. The universe became transparent. The photons were freed. That is the moment that produced the cosmic microwave background, the light that is now measured at 2.7 Kelvin. After that moment, the universe continued expanding and cooling. The first stars formed when the universe was roughly 100 to 200 million years old, igniting in the darkness and beginning the process of reionizing the universe's hydrogen with their ultraviolet light. Galaxies assembled over billions of years. Stars were born, lived, and scattered their synthesized elements back into the interstellar medium. New generations of stars formed from that enriched material. Planets formed around those stars, and on at least one of those planets, around one of those stars, a species arose that developed the technology to measure the temperature of the universe's oldest light, 2.7 Kelvin. The echo of the beginning, cooled by expansion across 13.8 billion years, still detectable, still setting the floor of cosmic cold, against which every star, every planet, every warm organism is a temporary, glowing exception. The relationship between the sun and the cold of space also determines the fate of Earth's energy resources in a very direct sense. Almost all the energy that powers life on Earth, with the exception of geothermal energy from the planet's interior and nuclear energy derived from radioactive elements, ultimately comes from the sun. Photosynthesis captures solar radiation and stores it in chemical bonds. Plants, algae, and cyanobacteria have been doing this for over 3 billion years. The coal, oil, and natural gas that powered the Industrial Revolution are the compressed, transformed remains of ancient organisms that once captured solar energy through photosynthesis. When those fuels are burned, they release the energy those organisms stored from sunlight that fell on Earth millions and hundreds of millions of years ago. Solar panels capture sunlight directly and convert it to electricity. Wind turbines harness the kinetic energy of air masses, set in motion by the unequal heating of Earth's surface by the sun. Hydroelectric dams capture the energy of water lifted by evaporation, which is driven by solar heating of the oceans, as it falls back down. Even the food you ate today ultimately traces its energy back to solar radiation absorbed by plants or by the organisms that ate them. The sun is not just the reason Earth is warm enough for liquid water. It is the source of essentially all the energy that flows through Earth's biosphere, and it is hot and Earth is warm, because the cold of space provides the necessary contrast. Without the cold of space, there would be nowhere for the sun's energy to go. Without that temperature gradient, hot sun, cold space, warm Earth in between, there would be no energy flows, no weather, no photosynthesis, no life. A universe that was uniformly warm at any temperature would be a dead universe. Not because warmth itself is hostile to life, but because life, and all processes in general, requires energy to flow. Energy flows from hot to cold. If everything is the same temperature, energy does not flow. No work can be done. No chemistry can proceed irreversibly. No information can be processed. No life can exist. The cold of space is not just the backdrop to the sun's warmth. It is a necessary condition for the warmth to do anything. It is the thermodynamic contrast that makes energy useful. The sun pours energy into a cold universe. Earth catches some of that energy in its warm middle ground between the fire and the void. And in that middle ground, extraordinary things happen. Chemical complexity arises. Evolution proceeds. Stars are observed, measured, and understood by the very matter they forged. The coldness of space is not the enemy of warmth and life. It is what makes warmth and life physically possible. The way human technology has learned to use the cold of space as a resource extends well beyond infrared telescopes and spacesuits. Researchers working on quantum computing and quantum communication face a fundamental challenge. The quantum states that carry and process information are extraordinarily fragile. They are disrupted by any interaction with the environment, by vibrations, electromagnetic noise, and most critically, by thermal energy. At room temperature, atoms and electrons are vibrating energetically. Their thermal motion constantly disrupts the delicate quantum coherences that quantum computing relies on. To keep quantum systems stable long enough to perform computations, they must be cooled to temperatures far below anything in the natural universe, typically to millikelvin range, just thousandths of a degree above absolute zero. The most advanced quantum computing platforms use dilution refrigerators, devices that exploit the mixing of different isotopes of helium at ultra-low temperatures to reach temperatures of 10 to 20 millikelvin. At those temperatures, thermal noise is reduced enough that quantum bits can maintain their states long enough to perform useful computations. These refrigerators are among the most extraordinary engineering achievements in modern physics. They create environments colder than anything found naturally in the observable universe, inside a laboratory on a planet orbiting a star that is itself 16 times hotter at its surface. The cold of space, at 2.7 Kelvin, is too warm for this purpose. The cosmic microwave background, the universal floor of cold, is itself too energetic for quantum computing. The most advanced quantum computers must be colder than the universe itself. This is a remarkable fact. It means that some of the most sensitive technology humans have ever built requires conditions that the natural universe does not spontaneously provide anywhere we know of. It requires us to engineer cold beyond the cold of deep space. The coldness of the cosmos, the 2.7 Kelvin of the vacuum, is in this context not the ultimate in cold, but merely the starting point for going even further. Humanity has extended the temperature scale beyond what nature provides at the low end. The same way our thermometers extend beyond what exists naturally at the high end. We have created environments hotter than any natural stellar surface in particle accelerators. And we have created environments colder than any natural void in physics laboratories. The universe set the boundaries. We have gone beyond them. The thermal environment of the space between galaxies, the intergalactic medium, is even more extreme in its sparseness than the interstellar medium within galaxies. The intergalactic medium fills the vast majority of the volume of the universe. It is the substance of the cosmic web, the diffuse gas that connects galaxies into filaments and sheets surrounding the great cosmic voids. Most of the normal matter in the universe, the protons, neutrons, and electrons that make up atoms, is not in stars or galaxies, but in this intergalactic medium. It is extraordinarily sparse. A typical region of the intergalactic medium contains perhaps 1 particle per cubic meter. Not per cubic centimeter, per cubic meter. Compare that to interstellar space within a galaxy at 1 particle per cubic centimeter. And you've already crossed a factor of 1 million in density reduction. Compare it to air at sea level and the difference is roughly 25 orders of magnitude. A volume the size of your bedroom, filled with intergalactic medium, would contain fewer particles than you can count on one hand. This medium is not cold in the straightforward sense. Observations by X-ray space telescopes have shown that much of the intergalactic medium, particularly in the denser filaments of the cosmic web, is hot. Temperatures ranging from 100,000 to 10 million Kelvin. This gas was heated by the same processes that formed the cosmic structure. Shock waves from the gravitational collapse of matter into filaments and galaxy clusters, feedback from active galactic nuclei, and supernovae within galaxies. But as with the interplanetary plasma and the interstellar hot medium, these high particle speed temperatures do not translate into warmth in any experiential sense. The density is so low that the thermal energy content per cubic meter is negligible. An object placed in the intergalactic medium would cool to the temperature set by the radiation field around it, primarily the cosmic microwave background, with some contribution from the diffuse radiation of surrounding galaxies. In the densest parts of galaxy clusters, the intergalactic medium, called the intracluster medium in that context, reaches temperatures of tens of millions of Kelvin and densities high enough to produce significant X-ray emission. The Perseus cluster, a massive galaxy cluster roughly 240 million light-years away, has an intracluster medium heated to temperatures around 50 million Kelvin. This medium is so hot and dense that it actually emits in X-rays at a rate detectable across cosmological distances. In 2022, the Chandra X-ray Observatory detected what appeared to be sound waves in the Perseus cluster's intra-cluster medium, pressure waves generated by the feeding of the cluster's central, supermassive black hole. Those sound waves, with a period of roughly 10 million years, had been propagating through the hot gas for hundreds of millions of years. But even in this extraordinary environment, where the gas is 50 million degrees and the very medium is ringing with ancient sound, the overall energy density per cubic meter is modest. The vast majority of the cluster's volume is empty. The gas is hot, but thin, and in the regions between clusters, where the cosmic web filaments thin out into true voids, the intergalactic medium drops back toward 2.7 Kelvin. The cold is always there, waiting in the spaces between the hot concentrations. The default state of a universe that has been expanding and cooling for nearly 14 billion years. The implications of all this for how we think about the sun extend in a direction that is easy to overlook. The sun is often described as middle-aged, halfway through its 10 billion-year main sequence lifetime. That framing is accurate but incomplete. The sun did not appear from nothing 4.5 billion years ago. It formed from a cloud of gas and dust, the solar nebula, that was itself assembled from the remnants of earlier generations of stars. The hydrogen in that cloud was primordial, created in the Big Bang. But the heavier elements, the carbon, the oxygen, the iron, the silicon that make up Earth's rocks and your body's chemistry, were forged in the nuclear furnaces of massive stars that lived and went out billions of years before the sun existed. Those stars poured their energy into the cold of space, lived their brief, intense lives, and scattered their synthesized elements in supernova explosions. The cloud that formed the sun and the solar system was seeded with those stellar ashes. The sun itself formed when a region of that cloud collapsed under its own gravity. As the cloud contracted, it heated. The gravitational energy of collapse converted to thermal energy. The center grew hotter and denser until, roughly 4.5 billion years ago, The temperature and pressure were high enough for nuclear fusion to begin. The sun ignited. From that moment, it has been radiating its energy into the cold of space, warming the planets in its vicinity and slowly converting its hydrogen into helium. The sun is not a permanent fixture. It is a stage in the life cycle of matter, the transformation of primordial hydrogen into heavier elements, the temporary concentration of energy before its inevitable dispersal into the cold. Every photon the sun emits today is carrying a fraction of the energy that was stored as mass in hydrogen atoms when the Big Bang created them. That energy is slowly being unlocked, used to warm planets and drive biology, and ultimately released into the cold of space where it will spread and dilute until it is indistinguishable from the cosmic background. The sun is a machine for converting mass into light and light into entropy. It is beautiful and powerful and the source of essentially all the energy available for life on Earth. And it is temporary, as are we. As is everything that depends on its warmth. The cold of space is not just the present condition. It is the eventual condition of everything. Stars burn, energy disperses, the universe expands, entropy increases, and the temperature of the cosmos, already close to absolute zero, edges incrementally lower with every passing billion years. The warmth we live in is not a steady state. It is a transient, a flicker in the long, cold story of the universe. A story that began in fire is passing through warmth and will end, after an almost incomprehensible span of time, in a cold so absolute and so complete that the concept of temperature itself will barely apply. Return, finally, to the original image. You standing outside at night, looking up at a sky full of stars. Each one is a furnace. Hundreds of billions of them in our galaxy alone. The light, reaching your eyes right now, left those stars years, decades, centuries, sometimes thousands of years ago. It has traveled through a near-perfect vacuum the entire way, losing almost none of its energy, disturbing almost nothing it passed through. And the space it traveled through, the space it is still traveling through, is near absolute zero. Not because the stars are not powerful, not because the light is not real, because space is not a container that holds heat. It is not a fluid that warms when energy passes through it. It is the absence of the thing that temperature describes. The photons you see carry energy from fires burning at millions of degrees. They arrive at your eye and convert their energy to a tiny cascade of electrical signals in your retina. And the space they just crossed, the space 1 centimeter in front of your face, is still 2.7 Kelvin. The warmth is in the photon. The cold is in the absence of matter that surrounds it. Both of these are always true at once. The sun burns. Space does not warm. And the reason, stripped of everything else, is that heat requires something to be hot. Space is nearly nothing. And nearly nothing cannot hold a temperature. It can only be the stage on which temperature and matter and light and everything else that is something briefly exists. There is a thought experiment that gets at the heart of all of this in a way no equation quite can. Imagine you are floating in deep space, far from any star. Not just far from our sun, far from every star. Out in the intergalactic void, where the nearest galaxy is millions of light years away, and the nearest star within that galaxy is light years beyond that. You are suspended in nearly perfect darkness. The photons around you are so sparse that you might go minutes between one striking your skin. The temperature reads 2.7 Kelvin. You are, for all practical purposes, as cold as the universe gets. Now, a photon from a distant star finally reaches you. It strikes the retina of your eye, in your brain, A cascade of electrochemical reactions converts that photon into a signal. You see a point of light in the darkness. That star is burning at perhaps 10,000 Kelvin. Its corona may reach millions of Kelvin. It is converting millions of tons of hydrogen into helium every second. And yet, the space between you and it is still 2.7 Kelvin. The photons, carrying the light from that star, have crossed hundreds of light years of vacuum without warming it in the slightest. They carry energy, they do not carry temperature. Because temperature belongs to matter, and between you and that star, there is almost none. This is the universe as it actually is. Not the universe of our intuition, where hot things make their surroundings hot, where fires warm rooms and suns warm planets. The universe of physical reality, where heat is a property of particles, where warmth requires a medium, and where the vast majority of existence contains no medium at all. The story of how we learned this is as fascinating as the physics itself. For most of human history, the cold of space was simply assumed rather than understood. Ancient astronomers looked at the night sky and understood that the stars were far away. They did not, could not, know what that distance actually meant for temperature. When Isaac Newton described the laws of motion and gravity in the 17th century, he made it possible to calculate the distances to planets and, eventually, to estimate the distances to stars. But temperature, in the modern sense, barely existed as a concept. The thermometer was invented around the same time as Newton's Principia, and the idea that heat was related to the motion of particles was still decades away from being properly articulated. The kinetic theory of gases, which provides the correct framework for understanding why space is cold, took shape in the 19th century. James Clerk Maxwell and Ludwig Boltzmann worked out the mathematics of how temperature emerges from the statistical behavior of enormous numbers of moving particles. Their work made it possible to understand, for the first time, why a perfect vacuum has no temperature in the conventional sense. If there are no particles, there is no kinetic energy to measure. If there is no kinetic energy, temperature becomes undefined rather than simply zero. This was a conceptual revolution. Cold space was not just cold. It was something stranger. It was a place where the ordinary concept of warmth ceased to apply. The discovery of the cosmic microwave background in 1965 added another layer to this understanding. When Arno Penzias and Robert Wilson first detected that persistent hiss of microwave radiation coming from every direction equally, they did not know what they were looking for. They checked their equipment repeatedly. They removed a pair of pigeons that had nested in their antenna and cleaned out what they diplomatically called white dielectric material. The hiss remained. It was only after they contacted researchers at Princeton, who had been actively searching for the exact signal Penzias and Wilson had stumbled upon, that the significance became clear. This was not noise from their equipment. This was light from the Big Bang itself, stretched by 13.8 billion years of cosmic expansion into microwaves, filling the universe uniformly from every direction. The temperature of this background radiation was 2.7 Kelvin, not zero, not negative 270. 2.7. A number that tells us the universe has been cooling from its initial fireball state ever since the beginning, and that it is not finished cooling yet. In 5 trillion years, when the last stars have burned out and black holes have begun their long evaporation, the background temperature will be lower still. The universe is on a slow, one-way journey toward absolute zero. It will never quite arrive, but it is always moving in that direction. The photons from the Big Bang, now detected by our satellites as a faint microwave glow, are perhaps the ultimate answer to the question this video began with. Why is space so cold when the sun is so hot? Partly because the sun's warmth does not penetrate a vacuum, but also because space was cold long before the sun existed. The universe was born hot, 10 to the 32 Kelvin in its first instant. It has been cooling ever since. The sun is a temporary reversal of that trend, a pocket of heat in a universe trending cold, a local exception in an environment that is, at the largest scale, in the slow and relentless process of dying. Consider what this means for the night sky you see from your backyard. Every star you can see with the naked eye, all roughly 5,000 of them on the clearest possible night, represents a temporary island of heat in an ocean of cold. The spaces between those stars, the darkness you see when you look away from them, that darkness has a temperature of 2.7 Kelvin, not the absence of temperature, a temperature, the temperature of the afterglow of creation. The space between the stars is not empty of radiation. It is filled with the oldest light in the universe. You are, at this very moment, being bathed in photons that were emitted when the universe was 380,000 years old. They have been traveling for 13.8 billion years. They are arriving at your skin right now. They carry almost no energy. You cannot feel them. But they are there. The cold of space is not the absence of light. It is the presence of the oldest light that exists, so redshifted by expansion that it has become invisible to your eyes and nearly impossible to feel. The universe is not dark. It is glowing at 2.7 Kelvin in every direction. We just cannot see it without instruments built specifically for the task. There is one more dimension to this story that deserves to be told. The question of why space is cold is, underneath everything, a question about what the universe is made of. We tend to imagine the cosmos as a place full of stuff, stars, planets, galaxies, nebulae, the spectacular imagery we associate with space exploration. But the actual universe, measured honestly, is almost exclusively nothing. The observable universe stretches roughly 93 billion light-years across. Within it sit perhaps 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. These numbers sound enormous. They are enormous. And yet, if you could take all the matter in the observable universe and spread it evenly through all the space it occupies, you would end up with roughly 6 hydrogen atoms per cubic meter. 6 atoms per cubic meter. The air you are breathing right now contains about 25 billion atoms per cubic meter. Compared to your lungs, the average density of the universe is not even a whisper of thinness. It is incomprehensibly less than that. This is why space is cold. Not because the sun fails to shine. The sun shines brilliantly, not because heat does not exist. Heat exists in extraordinary quantities in the hearts of stars. But because the matter required to host that heat, to receive it and hold it and radiate it outward into the experience of other matter nearby, is so sparse, so vanishingly rare across the vast distances of the cosmos, that most of the universe simply has no capacity for warmth. The universe is not cold because it is far from heat sources. It is cold because it is mostly made of nothing, and nothing, as it turns out, cannot be warm. We began with a simple observation. The sun burns at millions of degrees in its outer atmosphere, and the space it burns inside is nearly at absolute zero. The answer is not complicated once you have the right framework. Heat is motion in matter. It requires particles. It requires collisions. It requires something to carry it and something to receive it. Remove the matter, as space so thoroughly does, and there is no mechanism left for heat to exist in any experiential sense. The photons from the sun race through the vacuum at the speed of light, carrying energy without warming anything around them. The corona burns at 3 million Kelvin but is too sparse to warm a fingertip. The cosmic microwave background fills every corner of the observable universe at 2.7 Kelvin, the last echo of a beginning so long ago that the light from it has been traveling since before the Earth or Sun existed. The darkness of the night sky and the cold of space are the same phenomenon, both consequences of a finite-aged, expanding universe spreading its energy thinner and thinner across a volume that grows without end. The cold of space is not a mystery once you understand what heat actually is. It is the inevitable, natural state of a universe that is mostly empty, slowly expanding, slowly cooling, with small, temporary, brilliant exceptions scattered across it at enormous distances. Those exceptions are the stars. We happen to orbit one of them. That is not nothing. It is, in fact, everything. Every atom in your body was forged in the interior of a star that ended its life billions of years ago, scattering its contents into the cold. The universe assembled those atoms, on this planet, in this configuration, close enough to a star to stay warm, with an atmosphere thick enough to hold that warmth in. In the deep cold of a universe hovering 2.7 degrees above absolute zero, that is an extraordinary piece of physics. The universe is cold. You are not. And the distance between those two facts is a story still being written, one photon at a time. If this journey into the physics of heat and the cold of the cosmos left you with something to think about, something you did not know before you pressed play, consider sharing it with someone who might feel the same wonder. The universe keeps its secrets close, but every now and then, asking a simple question opens a door into somewhere far more extraordinary than the question itself suggested. Stay curious. The cosmos has not run out of surprises.